Yeah, least
that
disk.
cannot be there,
Yes,
no, ma'am.
our
For
experiment is yeah. Our experiment is least disk only, no?
this.
Least disk, and this temperature will transfers from uh, heat temperature transfers from stream box to least disk. When it will transfer?
When we remove the bad conductor.
Yes. So this is only happens there. This process only happens in that experiment, and also isochoric process also we have in that whatever we are completed in these 6 experiments, right? So you understand that anybody read isochoric process, if you will get any idea in our 6 experiments, whatever learn in our experimental in our labs, that is only we will discuss in total syllabus we have in that only. Okay, so you all of you see here, dw is equal to pdv is equal to 0. Okay, where we will get here value? Think where we will get here value.
Constant, ma'am.
Volume in 6 experiments. Volume we will get in quill tube. Where which experiment is this one? This quill tube experiment is which one? Boiled law. Okay.
Boils.
Yeah.
Yes, yes, ma'am.
There we will take. There we will get that value, right? So and this cycling process. Cycling process. Since the system runs to its initial state, we will take their initial temperature also, we will note in that experiment, to particularly mixture method.
Yes, ma'am.
In mixture method, first what we will take the temperature, first we will go to initial temperature. After
Temperature.
that, yes,
Initial temperature, then after we in that
T2.
box some balls, no, ma'am.
Yes, mixture balls, yeah, solid balls.
uh, Whenever it will be constant at a particular degree, we'll take that temperature. Then after, in that wooden box, we will take 50 ml of water.
That is called calorimeter. Okay. In
Calorimeter.
that we will take before only we will take 50 ml water. So after T2, where we will take that steady temperature of that T2 of solid material. After that, what we have to do? That whatever the T2 solid material is there, that way we will take, and we'll where we will take this solid material in that calorimeter, isn't it?
Yes, yes, ma'am.
Yeah, already in that calorimeter we have 50 ml of water. What will happen in that experiment? After that it will cooling, then it will come down
To
again
the
T1.
same.
Same.
Yes, ma'am.
T1, T2, T3, again T1, T2, T3, like that will go. So that's why we are telling we used in that experiment this cycling process only. There, that is the first law of thermodynamics. dq is equal to du plus dw. Okay. So isobaric process also we have in another experiment. We'll discuss later. And we discussed reversible and irreversible process also. In that we can see little bit about this reversible irreversible process. We see so many changes happens around us every day. Okay, and such as boiling water, rusting of iron, melting ice, burning of paper, etc. Every day we will see this any some situation, right? Okay.
Yes, ma'am.
Okay. So, and here now, for how many such systems surrounding of brought all these some examples also we discuss about this reversible irreversible process, and conditions of reversible and example of reversible. Irreversible process. Today we'll go for, see all of you observe the screen. The differences between these two reversible and irreversible process. Anybody can you read this between these difference between these two reversible and irreversible? Are you able to see the screen?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Anybody please. When you are active in a class, I will also active, right? So that's why anybody can you read this? You are able to see this, no? What about reversible process happens?
The process occurs infinitesimally slowly.
Yeah. What happened here in reversible? For
The
example, whenever we are running in reverse, what will happen? We will go fast or slowly we will run now?
slow,
Yeah, slow. That here also that will happen. And irreversible, it is very
like
fast, right? We are
yes, ma'am.
moving forward. We are running forward. That's why it will move very rapidly. And here, what about equilibrium in reversible process? What about equilibrium in reversible process?
Not disturbed.
Yeah, equilibrium process is not disturbed means what will happen there? It is not the temperature will increase and decrease. And here also irreversible process may be alter, may be attained only after process completion only. We will see the equilibrium process in this irreversible. Okay, and what will happen in reversible? Work done is the maximum will happen here. Work done is not maximum. It will complete, it will come. Work done is there, but it is not in maximum. Okay, can be easily reversed. When you will get this question, you will able, if you read this, if you will able to write the, at least you will attempt the questions. Okay, and can be easily reversed and can be easily same process cannot here and can here. Okay, and same thing here, and we will get that. Yeah, second law of thermodynamics also we discussed in last class. And what is the second law? We have some statements are here in this second law of thermodynamics. So one is a Clausius statement and Kelvin Planck statement. This is very important, and entropy statement. Okay, what is the Clausius says? Heat cannot spontaneously flow from a colder body to a hotter body. Anybody can you give example of this statement? Heat cannot spontaneously flow from a colder body to a hotter body. Anybody? Where the temperature will spontaneously increase, where the temperature spontaneously colder body to a hotter body. Yeah, same example of for this Clausius statement. This is the same example of where solid mixture method. We will take this example here. And what about the Kelvin Planck statement? Kelvin Planck statement. So here, what will happen in Kelvins? So it is impossible for any device that operate on a cycle to receive heat from a single reservoir and produce the net amount of work. So he given this statement, and entropy statement also we have here. The entropy of an isolated system never decreases. It either remains constant in a reversible process or increases in an irreversible process. These statements are very important in second thermodynamic law. Okay, and here mathematically we are proving that delta U is equal to Q minus W, where we will take a delta U is a change in internal energy of the system. Q is the heat added to the system. W is as usually work done. Okay, finally we will tell that dQ is equal to du plus dw or du is equal to dq minus dw. This is first equation. And here mathematically here second, what is the second equation? This is the process to
Quantity of heat.
yes, mathematically for reversible process based on corner theorem, we'll take that dq is equal to tdn. After that, again, I will ask in between the listen. dq is equal to tds if you want to write these equations. If p represent what p represent here? We don't have any p here, no?
Pressure and volume, ma'am.
Yeah, here in that third equation, pressure and volume represent the work done on the system. dW is equal to work done and P is the pressure and V is the volume.
Volume.
Yeah, substitute these equations to 2 and 3 in one first equation. What is our first equation? du is equal to dq minus dw or dq is equal to du plus dw. Okay, how we are getting this minus? I think so you are all understand this equation. Then it will come here, this is a minus will come. And suppose for example we are substituting these two equations 2 and 3 in first equation. What will we will get here? EU is equal to TDS minus PDV. Okay. So
Yes, ma'am.
this equation is called the first statement. What is our first statement? Classius statement. Okay. Differential relation. This equation applies to the closed system performing PV work only here. Okay. And
Pressure and noise.
yeah, and application of second law of thermodynamics, heat engine model, we are taking the application. What will happen in heat engine? Uh, the second law of thermodynamics is the heat engine model. This is one example we are taking for second law of thermodynamics. Heat engine involves a cycle of increasing and decreasing temperatures. Okay, that moves a piston. The second law of thermodynamics dictates the amount of work that the changing temperatures in the heat engine can be. This is one example of this second law of thermodynamics. Okay, this is also we discussed in last. And come to the main point is thermodynamic potentials. Okay, this is also very important question. Yeah. What is thermodynamic potential? The thermodynamics potentials, also known as thermodynamic functions, are state functions, are fundamental concepts in thermodynamics that helps describe any analyzing the behavior of the physical systems. In first class, we discuss about the systems. We have three systems: closed system, open system, and
Isolated system.
Very good, Amma. Isolated system. So here also we are discussing in these thermodynamic potential. These potentials provide valuable insight into the thermodynamic properties of a system and how they change under different conditions. The temperature will change, decreasing and increasing point. They are mathematically functions of state variables such as temperature, pressure, volume, and composition. Okay, and can be used to derive the relationship between the various thermodynamic potentials. Okay, we have here thermodynamic potentials are U, H, F, G. Okay, so what is U? U, we are indicate this U is the internal energy. What is the internal energy? Internal energy is the total energy contained within a system. For example, internal energy. We want energy. We are losing the energy. What we can do? Real example, anybody you tell me that. What you understand about this point? Internal energy is the total energy contained within a system. We are only systems, for example. Anybody can you tell that? What, how it will internal energy contains?
I think
Yeah. Any
in
example, real example, one, real life example only.
summer, when we go out, our energy levels will be getting down. So to regain some energy, we'll drink some liquids.
Okay. For example,
Like
here, yeah, continue. Yeah, tell me, ma. Check.
అంటే ఎప్పుడైతే మనము ఎండకి వెళ్తామో మనం ఒక సిస్టమ్ అయినప్పుడు మేడం ఇంటర్నల్ గా మనకు సమ్ ఎనర్జీ అనేది ఉంటుంది. ఆ ఎనర్జీ ఎప్పుడైతే మనము సమ్ వర్క్ డన్ చేసినప్పుడు కానీ వర్క్ చేసినప్పుడు కానీ మన ఎనర్జీ డౌన్ అవుతే ఐ మీన్ వీల్ రీగైన్ అవర్ ఎనర్జీ బై డ్రింకింగ్ ఆర్ టేకింగ్ సమ్ ఫుడ్ ఐటమ్స్.
Cycle process will go on there, right? Okay. And here, that example very good. This example very useful to you. And also here, what is the system? System is only very weak, right?
Yes, ma'am.
Yeah. For example, everybody use in winter time. We used for temperature. What we will use heaters. We will use there, right? For
Yes.
example, we are staying in one room. Okay, there we will take that heater, room temperature, room heater. What will happen there? That is a closed system. For example, what will happen? Total heat or temperature covered in that closed system only, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
Yeah, here also, including this both kinetic and potential energies of its particle, it is a function of temperature, volume, and the number of particles. Okay, changes in internal energy can be related to heat transferred and work done on or by the system. Okay, and here enthalpy H. What is the enthalpy? What is the work of enthalpy? Enthalpy is the sum of internal energy and the product of pressure and volume. It is often by in analyzing process at constant pressure and provides insights into the heat transfer under those conditions. Okay, I think you are understanding about this enthalpy. Okay, what you understand about this definition, Amma? మీకు మీరు ఏం అర్థం చేసుకుంటున్నారు ఇది ఎంథాల్పీ అంటే ఏంటి ఎంథాల్పీ is the sum of internal energy and the product of pressure and value. Okay, here also we are seeing in internal energy, it is a function of temperature, value. Here also what we are taking pressure and volume in enthalpy. You remember that here we are taking T and V in internal energy. Okay, here in enthalpy we are taking P and V. T and V and P and V. We'll see in later.
Energy.
Yeah. Here and also F also is there. What is F? What is F? Helmholtz free energy. What we use in this Helmholtz energy? This is the free energy. This is defined as the difference between the internal energy of a system and the product of temperature and entropy. What we are taking here? Temperature and entropy. It is particularly used for the system at constant temperature and value. Okay. Here in internal energy, what we are taking T and V. In enthalpy, P and V. And here what we are taking T and V also we are taking. But where we are taking this? It is particularly useful for the systems at constant temperature only. Okay. So, and also helps predict whether a process will occur spontaneously. Whenever we will get the temperature spontaneously, we will use this Helmholtz free energy. Okay. And here Yeah, gives free energy, that is U. Okay. What words we are taking? U, H,
F
F
and G.
and G. Okay. What is the Gibbs free energy? Gibbs free energy is the difference between the enthalpy and the product of temperature of enthalpy. Here also same. Okay. But here difference between the internal energy of a system. Here in Gibbs free energy, what will tell us?
Enthalpy.
Difference between the enthalpy and the product of temperature and entropy. Here also same, but the difference between the internal energy, Helmholtz energy, here enthalpy and the product of temperature and entropy. Yeah, it is used to analyze a system at a constant temperature. Are you able to understand this? In constant temperature and pressure. Here what we are seeing?
At constant
Yes,
Temperature and volume.
volume, here constant temperature and pressure. Okay. I think
Yes.
you are all understanding its words, right?
Yes.
So here now we are entering these formulas, whatever we have in our textbooks. So these are the internal energy, enthalpy, and there are two more we have here for first law. TDS is equal to du plus PdV. We'll write another is, what is the first law? What is the first law of thermodynamics? Anybody? What is the first law of thermodynamics? If you have open your textbooks.
Heat into work, ma'am.
Heat into
Work.
Yeah, heat into work, right? Yeah. So internal energy equation is du is equal to TdS minus PdV. U is equal to S and V. What is S here? Du is equal to internal energy. V pressure, temperature, volume. Okay. And here what is S ante we'll discuss later further in the equation. And enthalpy H is equal to U plus PV. We will write this dH is equal to TdS plus VdP. Here H is equal to SP. Internal energy U is equal to SU. Right? So the Gibbs function is, we will write that G is equal to U minus TS plus PV. Okay. H is equal to TS, G is equal to F plus PV. So you all of you observe these three equations, how we are getting this F plus PV. Here we have constant temperature and pressure and temperature and entropy, and here also temperature, we are changing the temperature and volume, and here pressure and volume. These terms only I am using here. Yes. Here, what are the properties of this Helmholtz function? F is equal to U minus T. Yes. And dF is equal to du minus T ds minus S dt. So we are taking here first law of thermodynamics. Du is equal to T ds P dV. What here? The formula of first law of thermodynamics. Du plus P dV. We are writing here. What will happen here? We are changing that. Du is equal to TdS minus PdV. And we are applying for this Helmholtz function. dF is equal to minus PdV minus S dt. We are taking F is equal to Helmholtz function is equal to volume and
Temperature.
Yeah. Come to the point of Gibbs law here. Tg is equal to du minus TdS minus S dt plus PdV plus VdP. So again we are taking for this Gibbs function, we are taking that first law, how we are writing du is equal to TDS PdV. du is equal to TDS minus PdV in Gibbs function. What we are writing here? du is equal to TDS minus PdV. Here TDS minus PdV. Okay. dg is equal to minus S dt plus V dP. We are taking G, temperature and P. Temperature and P are the constants in Gibbs function. Okay. Here Helmholtz functions, volume and temperature are the constants. Okay. Come to the point of internal energy. Here also, internal energy, what we are taking the constant? See.
Temperature and volume.
Temperature and volume, including the both kinetic and potential energies we are taking. Okay. Changes in the internal energy, temperature and volume we are taking. Right?
Yes.
Here also, you observe that here TDS minus P. Okay. So you think that du is equal to TV we are taking. Tp we are taking, temperature and pressure the constant, but we are applying this U is equal to S and V. Yeah, we are taking here from this equation du is equal to dou U by dou S suffix V ds plus du by dV suffix S dV. Then we are taking T in the place of T du by dou U by dou S suffix here V, and P is equal to pressure is equal to minus du by dV suffix yes we are taking. So Tp we are applying here. Yeah. Here what is G here? dG is equal to, we are using dF, the equation. See, dF by dV, T and V. We are taking these two. Right? Whatever constant we have here, we are taking suffix T and V. Here what we are taking the constant, you only tell me that P and T. Where we are taking this P and T constant? Pressure and temperature. What is G? Immediately you will get G. G means Gibbs. Okay. Yeah. Here dG by dt suffix P and V is equal to dG by dt TV. Okay. So finally we will tell that Gibbs and Helmholtz and what is that? Internal energy and again?
Helmholtz energy.
Helmholtz energy.
Enthalpy, Helmholtz and Gibbs.
Internal energy, enthalpy, Gibbs, Helmholtz. Kada? ఈ నాలుగు. Okay. So we will use that these equations are main equations for all these four. du. What is du? u ఎక్కడ తీసుకున్నాం మనం? Internal energy.
Internal energy.
Anybody write this? U is internal energy, enthalpy is the H, Helmholtz F, and Gibbs is G. Okay. Yeah. Finally, we will note down these equations. du is equal to TDS minus PdV. Here, what we are taking, the constants of S and V. Okay, for here. And H dH is equal to TDS plus VdP H S and P. ఇక్కడ చూడండి మీరు, all of you observe here in these four equations, whatever we have here, what we are taking? ఇది గమనిస్తున్నారు కదా, ఇందులో ఉన్నవి ఇందులో ఉన్నాయా, కాన్స్టెంట్ లో ఉన్నాయా?
Yes.
ఉన్నాయి మేడం.
ఇక్కడ టెంపరేచర్ కాన్స్టెంట్ ఉంది ఇంటర్నల్ ఎనర్జీలా కదా. ప్రెషర్ టెంపరేచర్ కాన్స్టెంట్ ఉన్నాయి గమనించండి ఇక్కడ అవి రెండు లేవు చూడండి కదా ఇక్కడ వాల్యూమ్ అండ్ టెంపరేచర్ తీసుకున్నాం కదా ప్రెషర్ లేదు ప్రెషర్ అండ్ టెంపరేచర్ తీసుకున్నాము వాల్యూమ్ లేదు ఇక్కడ చూడండి వాల్యూమ్ అండ్ టెంపరేచర్ ఆర్ ద కాన్స్టెంట్స్ ఇన్ దిస్ ఈక్వేషన్ dg is equal to minus sdt plus vdp and here temperature and p are the constants. All these four equations are the called as the thermodynamic potential equations. Okay, all these four called the thermodynamic potential equations. And here the Maxwell relations, how we will tell all these four equations. dt by dv suffix s is equal to minus dp by ds suffix v. అంటే ఇక్కడ what we are taking the constant s and p. Okay, what is the relation between these s and p? SNP లో మీకు ఏ రిలేషన్ కనపడుతుంది ఇంటర్నల్ ఎనర్జీ గిబ్సా ఏం కనపడుతుంది
ఇంటర్నల్ ఎనర్జీ
ఇంకా
జిప్స్ అండ్ ఇంటర్నల్ ఎనర్జీ మ్యామ్
ఇంకా
హెల్మ్హోల్ట్జ్ ఫ్రీ ఎనర్జీ
ఇంకా ఇవన్నీ కనపడుతుంటాయి ఇక్కడ మీకు చూడండి ఫోర్ ఈక్వేషన్స్ గమనించండి ఎవరన్నా
ఎంట్రోపీ కూడా ఉంది మ్యామ్ ఎంట్రోపీ కూడా
వెరీ గుడ్ వెరీ గుడ్ చదవండి ఫోర్ ఈక్వేషన్స్ ఎవరైనా మీకు తెలుస్తుంది ఏది కాన్స్టెంట్ అనేది మీకు ఇక్కడ ఎగ్జామ్ కూడా పనికొస్తుంది మీకు చదవండి అమ్మా ఎవరన్నా నేను చదువునా ఓకే నేను చదువుతాను సో ఇక్కడ మనకు ఈ ఎస్ అనేది క్వాంటిటీగా తీసుకుంటాం ఓకే సో డో టీ by dou v suffix s is equal to minus of dou p by dou s suffix v. ఇది గమనించండి మళ్ళీ నేను క్వశ్చన్ అడుగుతాను డో ఎస్ బై డో వి సఫిక్స్ టి ఓకే డో పి బై డో టి సఫిక్స్ వి ఈ ఈక్వేషన్స్ అన్ని 4 ఉన్నాయి కదా ఈ 4 ఈక్వేషన్ లో ఫస్ట్ ఈక్వేషన్ లో ఎస్ అండ్ వి కాన్స్టెంట్స్ తీసుకుంటామా టెంపరేచర్ అండ్ పి కాన్స్టెంట్ తీసుకుంటామా చెప్పండి ఫస్ట్ ఇంటర్నల్ ఎనర్జీలో టెంపరేచర్ అండ్ ప్రెషర్ కాన్స్టెంట్స్ తీసుకుంటాము ఇక్కడ వచ్చేసి టెంపరేచర్ అండ్ వాల్యూమ్ ఇక్కడ వచ్చేసి టీ అండ్ వి అండ్ ఇక్కడ వచ్చేసి టీ అండ్ పి దీస్ ఆర్ ఆల్ ద రిలేషన్స్ ఆఫ్ మ్యాక్స్వెల్స్ సో కమ్ టు ది పాయింట్ ఆఫ్ మ్యాక్స్వెల్ థర్మోడైనమిక్ ఈక్వేషన్స్ అండ్ దేర్ అప్లికేషన్ ఓకే మీ బుక్లలో ఉంటాయి ఇవి ఒకసారి చూసుకోండి మీ దగ్గర బుక్ ఉంటే కనుక okay the differential form of internal energy u will take du is equal to Maxwell relations amma malli confuse kavodandi these are the thermodynamic potential with using of that thermodynamic potential we are taking the Maxwell relations of these thermodynamic potential okay so here the differential form of internal energy u is du is equal to tds minus pdv. This equation resembles total differential of the form of we will take dz is equal to dou z by dou x suffix y ఇక్కడ ఏం లేదు మనము t and v ఎలా తీసుకుంటున్నామో సేమ్ ఇన్ డిఫరెన్షియల్ ఫార్మ్స్ we are using here dx plus dou z by dou y x అంటే ఇక్కడ మనము t and v తీసుకున్నాం కదా సేమ్ ఇన్ ద ప్లేస్ ఆఫ్ y and x we are using here okay for the total differential equations kosam it can be shown for any equation of the form dz is equal to m dx plus n dy ikkada dou z by dou x we are taking m idantha mottham kalisi m anukuntunam these are all the n we are taking so for example here we are taking that consider this equation du is equal to tds minus pdv ఇంటర్నల్ ఎనర్జీకి ఈక్వేషన్ చెప్పండి అంటేనే మీకు నిద్రలో కూడా యూ హ్యావ్ టు టెల్ du is equal to tds minus pdv. Okay, we can now immediately see that t is equal to, మీరు అబ్జర్వ్ చేయండి దీనికి you all of you observe here, m dou z by dou x suffix y, n dou z by dou y suffix s. Okay, suffix x, and t we are taking in the place of m dou u by dou s dou x v y. Okay, minus of p, ఇక్కడ ఇదే ఫామ్ రాస్తున్నా నేను కొత్తగా రాయట్లేదు. దిస్ ఈక్వేషన్ జస్ట్ ఐ am giving the derivation part of this one. Minus p dou u by dou v. ఓకే, ఇక్కడ dou s రాసినాం కాబట్టి ఇక్కడ సేమ్ తీసుకుంటాం చూడండి, dou u by dou s, t ని బయట తీసినాం, ఇక్కడ dou u by dou v suffix yes kada. Yeah, so here we are deriving that these Maxwell equations. Since we know that the functions of continuation second derivative and the maximum partial differential equations, we identify that dou y by dou y, ఇక్కడ dou by dou y differential equations I am writing here. Dou z by dou x y is equal to dou by dou x and dou z by dou y is equal to dou square by dou y dou x, that is equal to dou square z dou x by dou y. Okay,
x is equal to s, y అంటే v, z is equals to u.
ఇది నోట్బుక్ లో రాసుకుంటే మీకు అర్థమవుతుంది, రైటా?
మ్యామ్ ఎస్ మ్యామ్, y ప్లేస్ లో v మ్యామ్, x ప్లేస్ లో s మ్యామ్, z ప్లేస్ లో u మ్యామ్. t వస్తుంది, ఇక్కడ p వస్తుంది. స్పెషల్ అనుకోవచ్చు. t is equals to, మ్యామ్ మీ వాయిస్ రావట్లేదు మ్యామ్.
ఓకే, ఫైనలీ ఇప్పుడమ్మా
ఎస్ మ్యామ్.
finally dou t by dou v suffix s is equal to minus dou p by dou s suffix v. చూడండి ఇదే ఈక్వేషన్, జస్ట్ ఐఎమ్ డెరివింగ్ దట్ ఈక్వేషన్స్. ఓకే, అర్థమవుతుందా?
ఎస్ మ్యామ్.
సో డెరివేషన్ ఆఫ్
ఇక్కడ
చెప్పమ్మా.
లేదు మ్యామ్, ఇన్ ప్లేస్ ఆఫ్ డో యూ బై డో ఎస్ సఫిక్స్ వి ఈజ్ ఈక్వల్స్ టు టీ, కాబట్టి టీ బై ఎస్ మ్యామ్, అదే ఫార్ములా ఇక్కడ వచ్చేసింది, టెంపరేచర్ అండ్ ప్రెషర్.
ఇక్కడ ఏం నేను కొత్తగా ఏం పెట్టట్లేదు, ఐఎమ్ నాట్ అప్లైయింగ్ ఎనీ న్యూ ఈక్వేషన్, జస్ట్ ఐ డిరైవ్ ద differential equations from the relations of thermodynamic potentials with Maxwell relations. Okay, so here derivation of Maxwell relation from Helmholtz. Okay, ఇక్కడ du వచ్చింది కాబట్టి what is this? For the equation of internal energy, u, remember that. Okay,
yes ma'am.
yeah, Here now second one I am using here Helmholtz free energy. For that F I am using that word, right? Here.
Yes, ma'am.
Same equation I am applying here. dF is equal to minus of S dt minus P dV. S is equal to dou F by dou T suffix V minus P is equal to dou F by dou T. See, this is Helmholtz equation, right? This is Helmholtz equation. Yeah, sorry, internal energy equation. This is Helmholtz equation. ఇక్కడ చూడండి. Same అక్కడవే just I am replacing that equation, but I am writing here the differential equation of these Maxwell relations of thermodynamic potentials. Okay, minus S is equal to dou F by dou T suffix V minus P is equal to dou F by dou V. Here I am taking temperature and volume. Okay, that's why I am using that suffix also V and T. Okay, from symmetry the second derivation we are taking here dou V by dou F by dou T. ఇక్కడ చూడండి సేమ్ ఇదే ఈక్వేషన్ జస్ట్ ఐఎమ్ చేంజింగ్ దట్ Helmholtz ఫ్రీ ఎనర్జీ ఈక్వేషన్ సేమ్ దిస్ ఈజ్ ఓన్లీ మీరు ఇది రాసుకుంటే మీకు ఈజీ అవుతుంది ఫర్ ఎగ్జామినేషన్ టు ప్రిపేర్ ఓకే సేమ్ సి హియర్ వాట్ ఐ టుక్ హియర్ ఇన్ ఇంటర్నల్ ఎనర్జీ డో బై డో వి వాట్ ఐ టుక్ హియర్ డో బై డో వి
Dou
why
volume.
yeah here volume and pressure is the this pressure is the constant. Here what we have
Initial.
volume and temperature. Okay. Same this is equation
Yes, ma'am.
only. Just I am implying that Helmholtz equation here. Okay. So dou by dou v here dou u by dou s. Here what I took here Helmholtz free equation dou here internal energy u and here Helmholtz free equation energy f. Okay, and temperature. Okay, so dou f by dou
For all.
t, yeah, suffix v that is equal to dou by dou t. Here what I took dou by dou s. Here I took dou by dou t. Here pressure is the constant. Here temperature is the constant. Okay, and here internal energy for internal energy dou u by dou v I am taking here. Here for Helmholtz free energy is dou f by dou v. Okay, and suffix t. So same this is the form I use here also dou t by dou v suffix s here dou s by dou v suffix t and here minus of dou p by dou s suffix v here dou p by dou t suffix v. The other two Maxwell relations can be derived in the form of the enthalpy and Gibbs energy also we have no. Same similar way how we are getting these differential equations of this internal energy and Helmholtz energy. Then you try that you you do the derivation part of like this only. These two more we have no Gibbs free energy and enthalpy we have right. Total four potentials we have thermodynamic potential, internal energy U and Helmholtz energy F and enthalpy S and Gibbs free energy G we are taking right. You do these two derivations. You try it like this only same. Okay, what you will get see. If you have any doubt about these two doing that time, so you will ask the next class. Okay, I will clarify it, right? You
Okay,
try
ma'am.
it, this is a homework for you, right? Yeah. So the relations of thermodynamic potentials and differential forms and natural vibrations. See here say we have those four thermodynamics U, H, F, G and these are the equations. Anybody take if you want to take a photo or you can write this is okay. Okay na?
Okay, ma'am.
Yeah. Here again we have that same equations we are taking integral for internal part internal energy Maxwell's equation first one. We are taking U is equal to SV. Same these are the equations just I am showing that du is equal to how we will get the equation then internal energy du is equal to TdS minus PdV Consider now U as the function of enthalpy, yes, and volume V, such that these two we are taking for, we can now write the total differential of U SV. Okay. So du is equal to du dou u by dou s suffix v ds plus du by dv suffix s dv. Okay. This is the and also we are equivalent the expression of our du is equal to du by ds.
We are substituting du is equals to TDS minus PDT.
Very good, Amma, very good. So, same what we are getting here, same equations, right? So, I think so you are well understanding, right? Yeah. Coefficients, what we are taking, ds and du, right? So, here du by ds suffix v, t we are taking in the place of this, and du by dv suffix s in the place we are taking the p, right? So here again what we have the finally equation we will get dou by dou v suffix s, dou u by dou s suffix v is equal to dou t by dou v suffix s. How we are getting this one? We are using temperature and pressure here. So respect to V while keeping S are the constants. This means we are applying dou V by suffix S to the both sides for this equation. So we will get this equation dou U dou by dou V S dou U by dou S V, that is equal to dou U by ఈ equation ని రెండు సైడ్లు అప్లై చేస్తున్నాం అంతే. Okay. So finally we will get this equation. And here those same equations are written here. Again you express that the left hand side as dou S by V. This is the left hand side and this is the right hand side. So the order here we will get that. How you are understanding this equation? How I written here? Dou by dou S V. We have internal bracket also here. So dou U by dou V, dou by dou V suffix S. U is I'm bringing outside. Same this is right. And how I written here right hand side also? Dou by dou V, yes, dou by dou S suffix V U. Okay, U is outside I am bringing here. So finally what we can say that dou T by dou V suffix S is equal to minus of P. P unda ikkada meeku. That's why we are writing dou P by dou S suffix S. Okay, here T is equal to dou T by dou V suffix S is equal to minus of P kada idi. Dou P by dou S suffix V. Okay, yeah. So here what we have to take, that is the equation for
Internal energy.
Internal energy. Very good, you are following me, right? Good. So for enthalpy of maximal relation, same like that only we are deriving here. Same whatever we done, same here also for enthalpy I am taking that H, no, here. So H as the function of the neutral variables S and P we are taking just. Okay, H is equal to S and P. So we can find the total differential equation is the, ఇక్కడ చూడండి మీరు గమనించినారో లేదో, ఇక్కడ చూడండి du కదా, సేమ్ ఈక్వేషన్. ఈ ఈక్వేషన్ జస్ట్ ఐఎమ్ గివింగ్ ద రిలేషన్ ఆఫ్ మ్యాక్స్వెల్ ఈక్వేషన్. అర్థమవుతుందా? సేమ్ అదే ఈక్వేషన్సే ఐఎమ్ యూజింగ్ జస్ట్ ఎంథాల్పీ ఈక్వేషన్ హియర్. See, dH dou H by dou S pressure and we are taking the pressure and what is in enthalpy constants we are taking. Enthalpy lo ఏమేమో కాన్స్టెంట్స్
S and P pressure and
Pressure and volume.
volume. Very good. So here P and ds, same equation I am deriving here. So same formula. ఇవన్నీ మీరు చెయ్యండి ఇంట్లో ఒక్కొక్కటి తీసుకొని చేస్తే you will get right. ఇంకా మళ్ళీ మీరు ఎగ్జామ్ అప్పుడు మళ్ళీ ట్రై చేయాల్సిన అవసరం ఉండదు. ఒక ఈక్వేషన్ పట్టుకొని ఇప్పుడు చూడండి వాట్ ఐ సెడ్ హియర్ ఎంథాల్పీ కదా. ఎంథాల్పీకి ఐ డిరైవ్ దిస్ ఈక్వేషన్. ఇంటర్నల్ ఎనర్జీకి ఈ ఈక్వేషన్ తో ఐఎమ్ గెటింగ్ ఫైనలీ దిస్ ఈక్వేషన్. ఓకే, for enthalpy also I am getting this equation dou T by dou P suffix S is equal to dou V by dou S suffix P kada. So this is all the equation of whole head energy. This is another one. These are all the thermodynamic potentials only. Yes, just we are showing that we are deriving that the relations of Maxwell equations with the thermodynamic potentials. Okay, right? Yeah, this is for whole head free energy Maxwell relation. Same I am taking here df is equal to minus pdv by pdv minus s dt. Consider f is equal to vt, right? Equations lo f place lo పెట్టేయండి. Yeah, ఇది పెట్టేయండి. పెట్టేస్తే you will get that equation is the final one. And finally this is the equation of whole cell energy. So we will get the Gibbs free energy Maxwell relation also we will get same. dg is equal to v dp. ఒకటి తీసుకొని మీరు ఒక్కొక్కటి ఫైండ్ అవుట్ చేసుకుంటారండి. You will get. Okay, and while you understand this class, then only you can do this, right? If you are not understand whatever I am telling the equations, so you can't do, you cannot do this, right? You try it at home. Okay, and tell me in the next class. Okay, whatever you are doing this equation work. Okay, yeah, Gibbs free energy Maxwell relations, we will get the dou V by dou T suffix P is equal to minus of dou S by dou P suffix T. Okay, so finally we will get, these are the 4 equations. Okay na, ardhamaitundama? These are the finally dou U, here F, this is a sorry, F, this is dou F, dou H and dou Z. So dg, these are the thermodynamic potentials and these are the derivation of relations of Maxwell equation. Okay na? So right. So next class we will discuss latent heat. We have this is also in our syllabus. Next class we will discuss about the Carnot cycle and black body radiation. All this we will discuss in next class. Okay na? Right?
Okay, ma'am.
Okay, ma'am.
Okay, ma. Thank you. Right.
Thank you, ma'am. Thank you.
Okay, thank you.